Hey guys, today we're going to talk about counting theory with probability. Oh yeah. So, I've come up with this little problem. In the land of Narnia, there are 2 roads from the lamppost to the beaver's house, and 3 roads from the beaver's house to Cair Paravel. Well, basically, so if you start at the lamppost, then there's 2 different ways that can get you to the beaver's house. Okay, so I'm going to do that by symbolizing it with a B. And from the beaver's house, you can go 3 different choices to go to Cair Paravel. So I'm going to symbolize that with a C. Alright, so there we go. So this is the diagram that models this situation. Well, if I said, well, how many different ways can I get to Cair Paravel from the lamppost? You would say, oh, well, there's 2 ways to get to the beaver's house and 3 ways to get to Cair Paravel. So it sure does look like 1, 2, 3, 4, 5, 6 different ways to get from the lamppost to Cair Paravel. This type of diagram is called a tree diagram. And it illustrates the following property. It's called the fundamental counting principle. If an event M, big M, can occur in little m different ways, and is followed by event big N, which can occur in little n ways, then both events can occur in m times n ways, provided that the outcome of the first event does not affect the outcome of the second event. Okay, so basically, if we go back to our problem here, we had 2 ways to get to the lamppost and 3 ways to get to the, or 2 ways to get to the beaver's house and 3 ways to get to Cair Paravel. So that would be 2 times 3 ways to get from the lamppost to Cair Paravel. So that would be 6. Okay, well this principle can extend to any number of events. So it doesn't really matter how many different places you're trying to go or how many items you've got. As long as the outcomes do not influence subsequent events, then the type of event this type of event is called an independent event. Okay, so independent events are events whose outcome does not affect subsequent events. Okay, so here's an example. Too Cheap Computer Company sells custom-made personal computers. Customers have a choice of 11 different hard drives, 6 different keyboards, 4 different mice, and 4 different monitors. How many different kinds of custom computers can you order? Well, I can pick from 11 different hard drives, 6 different keyboards, 4 different mice, and 4 different monitors. So there's 11 times 6 times 4 times 4. That would be the counting principle, the fundamental counting principle that we're talking about. So 11 times 6 times 4 times 4 is, I'm going to come to my handy dandy computer, 11 times 6 times 4 times 4. Enter 1,056 different ways. Or 1,056 different computers. So if you were wondering why, like, different restaurants, for example, say they've got this many different things on their menu, this is what they're doing. They're multiplying the different types of options you've got by each other to get the different types of foods you can get. The Uptown Deli offers a lunch special in which you can choose a sandwich, a side dish, and a beverage. If there are 10 different sandwiches, so it would be 10 different sandwiches, 12 different sides, and 7 different beverages from which to choose, how many different lunches can you get? Well, that would be 10 times 12 times 7, which is, let's see, 10 times 12 times 7, 840. 840 specials. Okay, there we are. All right, let's try another one. Lily Brary has 5 different books that she wishes to arrange on a bookshelf. Well, how many different arrangements are possible? Well, we need to really think about this. I've got 5 different places for books on my bookshelf. In the first place, I'm going to have 5 different choices of books. But once I've put a book here, I'm only going to have 4 books to choose from here, 3 books to choose from here, 2 books, and I'm only going to have 1 book left for here. So my different arrangements are 5 times 4 times 3 times 2 times 1, which is 20 times 3 times 2 times 1, and that would be 60 times 2 times 1, and that would be 120. So there are 120 different ways to arrange the books. Okay? So, oops, kind of messed that up, that's okay. 120 different ways. So I want you to go to ET problem. This is your entrance ticket problem. That's what ET stands for, entrance ticket. Go to page 897 and do problem number 12. It would be like the problems that we've already done so far. Okay. The next thing, when we use the fundamental counting principle, we often work problems that have patterns, like the one that we just did, where it had that 5 times 4 times 3 times 2 times 1. Well, for convenience, we use this symbol. It's something that looks like this, in factorial, okay? In factorial, or it looks like this, for any positive integer in factorial equals n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. And 0 factorial is defined to be 1. So 0 factorial, we all just understand it to be 1. Don't try to rationalize it. That's just the definition. You can't have a negative factorial. That really doesn't make sense. And you just count down from the number that you start with, just all the way down to 1, and that would be your n factorial. So here's an example. Example 4. There are 8 students in the algebra club at Central High School. The students want to stand in line for the yearbook picture. How many different ways can 8 students stand for their picture? Well, let's think. We've got 8 different students, so we're going to have 8 different slots for them to stand. That's 6, 7, 8. And the first slot, 8 different people have the choice of standing there. Then 7, then 6, then 5, then 4, then 3, then 2, then 1. Now, by definition, this is 8 factorial. Okay? So, I'm going to come over here, and instead of actually writing 8 times 5 times 4 times 3 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 in my calculator, I'm going to use the factorial button. That would be 8, and come over here. Let's see, where did it go? I think it's right here. Is it right here? No. That's not it. Ha! I think on yours it's got a question mark and an exclamation point. We're going to use this exclamation point. There we go. And then we press enter and it gives us 8 factorial. Excuse me. Which is 40,320. So there's that many different ways for the students to stand for their yearbook picture. Wow. Mackenzie is setting up a display of 10 most popular video games from the previous week. If she places the games side by side on a shelf, how many different ways can she arrange them? Well, you'll probably say, well, that would be 10 factorial different ways. And I'm definitely going to use my calculator to calculate that. 10 factorial. And that is a really big number, 3,628,800. So that equals 3 million, and that I think was it, 628,800. That's a lot of different ways to put something on a shelf. Wow. Okay, Jill and Miranda are going to a national park for their vacation. Near the campground where they're staying, there are 8 hiking trails. Well, how many different ways can they hike all the trails if they hike the trails only once? Okay, well, that would be, well, 8 factorial, because they can go on 8 different hiking trails, and they're going to hike each one once. So the first one they would have would be 8, and then 7 choices, 6 choices, 5 choices, etc. And we've already done this one. This one's 40,320, if I believe. Pretty sure. Yeah. So there we go. They've got this many different ways they can walk the trails. If they only have time to hike on 5 of the trails, how many ways can they do this? Well, let's see what this means. We only have 5 slots, but in the first one they can choose from, they have 8 different choices to choose from. In the next one, they only have 7 choices since they've already gone down 1. Then they have 6 choices, 5 choices, and 4 choices, which would be 8 times 7 times 6 times 5 times 4. So 8 times 7 times 6 times 5 times 4. And that's 6,720. 6,720 ways that they can go down the trails if they only get to choose 5. Well, the number 6,720 in the previous example is called the number of permutations of 8 things taken 5 at a time. And we can write it as P of 8, 5. So if P of N, R denotes the number of permutations of N elements taken R at a time, where R is smaller than N, because you can only take, like if you're taking R elements, like here in the previous example, we took 8 trails, or 5 trails out of the 8. Your R is going to be less than or equal to your N, because you can't take more than what's there. Then, P of N, R equals N factorial over N minus R factorial. Because if you look at it, over here, what we had was 8 factorial, that was the number of choices, and we took off what was left over here. That would be 3 times 2 times 1, right? So that looks like 8 factorial over 8 minus 5 factorial. And 5 is actually the number of choices that we're choosing here, pieces that we're choosing. So this right here is permutation equation. And other ways that we can denote permutation notation would be P of NR, like that. That's one of the most common ways that it's seen. Another way that it's seen is where the N is on top, so like this, PNR. But this one's the one that you'll probably see the most of. Okay, on a test, a student must answer 7 out of 10 questions. In how many ways can a student order the 7 questions he chooses? So there's 10 different choices and there's 7 different questions that he can answer. So that's 10 factorial, and he's choosing 7, so that would be 10 minus 7 factorial, which is 10 factorial over 3 factorial. And I can actually use my calculator to find this. 10 factorial divided by 3 factorial. And that's 604,800. Okay, but what's kind of neat about this is if we look at it all expanded, 6, 5, 4, 3, 2, 1, divided by 3 times 2 times 1, these 3 cancel out with these 3. And then you can see that it's just the first 7 that we will look at. So go to page 897 and do problem number 15 in the book. All right. A concert pianist plans to perform 9 selections. In how many ways can she arrange the program? Well, she's got 9 selections and she's going to choose all of them. So that would be when R equals 9. So 9 minus 9 factorial is 9 factorial over 0 factorial, and 0 factorial by definition is 1. So this is just 9 factorial. So you just come over here and do 9 factorial, and that would be 362,800. 362,880, wasn't it? 880, yeah. There we go. So that's how many choices she can ways she can arrange her program. Here's one where we're looking at information and having to write something that's maybe a little more complicated. A new 3-digit area code is needed in a certain area to accommodate new telephone numbers. If the first digit must be odd, the second digit must be a 0 or a 1, and the third digit can be anything, how many area codes are possible? Now we're assuming that it can be whatever we want and we can repeat numbers. Well, let's look at the digits. Digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. 10 is not a digit. We can't use that. The first digit has to be odd, so the odd digits are 1, 3, 5, 7, and 9, which there's 5 choices. So the first digit must be odd. That's 5 different choices. The second digit must be 0 or 1, which would be this one or this one. And there's 2 different choices for that. And the third digit can be anything. Well, don't let this 9 fool you. There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total choices. So this would be 10. How many different area codes are possible? 100 different area codes. Okay, 5 times 2 is 10, times 10 is 100. Now we're going to draw a tree diagram to show the different area codes using 4 or 5 for the first digit. So I've got 4 or 5 for the first digit, 0 or 1 for the second digit, and 7, 8, or 9 for the third digit. So for the third digit, I've got 3 choices. Okay, now with this situation, I had 2 choices to begin with. I had 2 choices for the second digit and 3 choices for the third. So that would be a total of 12 choices. And here, as you can see, I have 12 choices listed. 407, 408, 409, 417, 418, 419, 507, 508, 509, and 517, 518, 519. Those are the 12 different choices for my area codes. So now, go to problem number, for your entrance ticket problem number 3, go to page 897 and do problem number 16. But what if order doesn't matter? And what I mean by this is, suppose there are 3 people, we'll call them Mr. Meller, Mrs. Doxtator, and Mr. Lister, that are applying for the 2 math club sponsors. Ignoring all other factors, in how many ways can Dr. Council select 2 people from the 3 applicants? Well, let's look. We've got Mr. Meller and Ms. Doxtator. We've got Mr. Meller and Mr. Lister. And we've got Ms. Doxtator and Mr. Lister. Okay, these are the only choices that I've got, because if I choose another one with Mr. Meller, we would have already done one with the other one, so I can't choose any more. I've already paired them all up, okay? So Meller Dox, Meller Lister, Meller and Dox Lister, okay? So these are the 3 different choices. So in how many ways can she select them? 3 ways. These 3 choices are called the combinations of 3 elements taken 2 at a time. So if N over R, in this kind of parentheses thing, denotes the number of combinations of N elements taken R at a time, where R is less than or equal to N, then N over R equals N factorial over N minus R factorial times R factorial. Okay, so let's see how we get that. Well, I have Mr. Meller can be in 3 different places, so that's 3 factorial. 3 different choices for him, for the different things. I'm choosing 2 of them, so that would be 1 factorial. But since I really don't care which order they're going to be in, I'm going to take that out. Whoops, take that out as a 2 factorial. and so that would give me 3. Okay? Well, how many different samples of 3 apples can be drawn from a crate of 25 apples? Well, since I don't care what order the apples come in, if I just take 3 clumps of apples, I don't care which apples are being taken. That would be, there's 25, that would be 25, choose 3, okay? That would be 25 factorial over 25 minus 3 factorial times 3 factorial, which is 25 factorial over 22 factorial, 3 factorial. And what I like to do with combinations is I like to go ahead and expand them out. 23, 22 factorial over 22 factorial times 3 factorial. And notice 22 factorials will cancel out. And here we have 25 times 24 times 23 over 3 times 2. And 3 times 2 and 24 simplify to 4, because that's 6 times 24 divided by 6 is 4. So that would be 2,300 samples. All right, because 24 times 5 is 100 times 23 is 2,300. Okay, well, in how many ways can a detail of 5 soldiers be chosen from a group of 14? Well, that would be 14. There's 14 soldiers, and I'm going to pick 5. Okay. Other ways we can denote combinations are in CR, or in CR, or C taking in comma R. All of these are different ways to denote combinations. Oh, I'm sorry, there's not a fraction bar in there. There we go. Okay, so we have 14, and we're taking 5, so that would be 14 factorial over 14 minus 5 factorial times 5 factorial, which is 14 factorial over 9 factorial times 5 factorial, which is 14 times 13 times 12 times 11 times 10 times 9 factorial over 9 factorial, 5 factorial, those cancel out, 5 factorial. I'm going to go ahead and expand this one. Is 5 times 4 times 3 times 2 times 1, and 5 times 2 is 10, so those go away, and 4 times 3 is 12, so those go away. So it's really just 14 times 13 times 11, and I mean, you can type it in either way. It's just easier for me if I know what's going on. I've got 14 times 13 times 11. And that's 2,200. So let's see. I've got 14,000 or 14 factorial divided by, that was 9 factorial times 5 factorial. And see, it's the same number. So you can do it either way, but I honestly want you to know how to simplify factorials here. So this is 2002. Now, in how many ways can the detail in Part A be chosen if it has already been decided that a certain soldier must be included? Well, what does that really mean? Well, out of the 14 people, we know one already has to be in there. So that means we now have 13 people left over and only 4 spots. So this is 13 factorial over 13 minus 4 factorial times 4 factorial, which is 13 factorial over 9 factorial 4 factorial. 13 times 12 times 11 times 10 times 9 factorial over 9 factorial times 4 times 3 times 2. Yay! Alright, 4 times 3 is 12. We can cancel that out and get a 5, and then 9 factorial, those go away. So it's 13 times 11 times 5. And that's 715. Wow. Okay. So now go to your problem number 4, do problem number 4, your ET problem number 4, go to page 898 and do problem number 28 in the book. A congressional committee consists of 4 senators and 6 representatives. A delegation of 5 members is to be chosen. In how many ways could this delegation include exactly 3 senators? Okay, so what we're talking about here is there must be, if there's 5 members that are going to be chosen, there has to be 3 that are senators, so that means there are 2 that are representatives. Okay? Well, in order to choose 2, let's see, in order to choose 4 senators, or 3 senators out of the 4, that would be 4 choose 3, and that would be 4 factorial over 1 factorial 3 factorial, which is just 4. And in order to choose 2 representatives out of the 6 of them, that would be 6 over 2, or 6 choose 2, and that would be 6 factorial over 4 factorial 2 factorial, which is 6 times 5 over 2, which is 15. So that means we have 4 ways to choose senators and 15 ways to choose representatives. So we're going to apply the fundamental counting principle, and that would be 4 times 15 ways to choose them, and that would be 60 ways to form the delegation. Okay? So, one of the problems with permutations and combinations for students is that they get confused in when to use which. So let's make a table to kind of help us decide. Well, permutations and combinations both are ways of selecting R items out of N items, and both say the repetitions are not allowed. But in permutations, we know that order is important. Okay. We also know that they are arrangements of R items taken from a set of N items. So these are arrangements of R items taken from N items. Okay? And the equation for permutations is P of N comma R equals N factorial over N minus R factorial. And some clue words that might help you know are arrangement, okay, schedule or order, okay. Those are some important words that would help you see if it was a permutation. For a combination, order is not important. Okay, and it's a set of R items taken from N items. Okay, so we're just taking a bunch of them and setting them aside. And a combination, N over R, combination of N items taken R items, N items and taking R of them, is N factorial over N minus R factorial times R factorial. And the clue words that would help you know if it's a combination are taking a group of something, a committee, a sample, or a selection. Okay, any of these would mean that you don't care what order you pick them in. So for this example, we're going to tell whether a permutation or combination should be used to solve it. Well, how many 5-card poker hands can be dealt from a 52-card deck? Well, let's think about this. When we deal out cards in poker, we just kind of go around the table and this person gets one and they just kind of get them and they don't look at them until they're done. So it really doesn't matter which order you get the cards in. When you look at them, it doesn't matter. So this is a combination. Okay. Letter B, how many different 3-digit numerals can be made with the digits 5, 6, and 7? Well, when we're talking about numbers, order matters because 567 is really not equal to 765. Okay, so that means order matters. So this is a permutation. And letter C, a sample of 3 light bulbs is randomly selected from a batch of 15 bulbs. How many different samples are possible? Well, if you noticed, it's talking about a sample, and we really don't care what order we pick the light bulbs in. We're just picking random light bulbs. So this is a combination. All right. So last one, go to page 898 and do problem number 32. Well, what do you do next? Once you've finished your entrance ticket, email me what the difference between a permutation and a combination is, and one good question that you need answered. And then what I need you to do is on class day, bring your completed notes and entrance ticket problems to class. And then we'll do problems from there. All right, see you guys later. Bye.